The first law of thermodynamics simply states that energy can be neither created nor destroyed. So in other words, the total energy of the universe is a constant. If a system loses energy, it must be gained by its surroundings. And if the surroundings, or if the system gained energy, the surroundings must have lost energy. Now, one of the most important ideas here that we need to get a handle on is the internal energy. Which is the sum of all kinetic and potential energies in the system. So if we considered the system with the hydrogen and oxygen reacting inside the cylinder, the internal energy would be all of the kinetic energy and all the potential energy of both the hydrogen molecules and the oxygen molecules. Now, it's not practical to calculate the total energy, but what we usually do is calculate the difference in energy. So the change in the internal energy of the system is equal to the energy final minus the energy initial. Right, like any other delta, it's always final minus the initial. The two pictures here depict, in the first case on the left, a final state that is lower in energy than the initial state, which means that the system lost energy to the surroundings. And the second one, the final state is at a higher energy state than the initial, which means that the system must have gained energy from the surroundings. The way in which we change the internal energy can either be through heat flow or work being done either by the system on the surroundings or by the surroundings on the system. So the picture here shows the system gaining heat energy and also gaining work energy, which means that the delta E, this system is going to be positive. So the final energy would be higher than the internal energy. And again, that delta E is dependent on the amount of heat that gets exchanged with the system and the surroundings and the work that's done either by the system on the surroundings or by the surroundings on the system. If we examine this equation more closely, Q, which stands for the heat exchange, Q would be positive if the system gains energy from the surroundings. Work is positive if work is done by the surroundings on the system. So the system is gaining energy due to work done by the system. So obviously if both of these were positive, that means we would have a net gain of energy by the system. Negative for Q means that the system loses heat. Negative for W means that work is done by the system on the surroundings. And negative, so then we would have a net loss of energy by the system. Now the heat exchange part, Q, is what we've referred to as endothermic and exothermic. So endothermic would mean that the system gained energy. We had to add energy to the system, so that would be Q would have a positive value. And exothermic would mean that heat was released from the system, so Q would be less than 0. The next idea we need to get comfortable with is the idea of a state function. A state function is a value that depends only on the present state of the system and not the path by which the system arrived at that state. So if you take the beaker of water in the middle here, the 50 grams of water at 25 degrees Celsius, the internal energy of that is the same regardless of that, arriving at that state from cooling down water that's a higher temperature or heating ice that was at a lower temperature. The internal energy of that beaker of ice would be the same. So internal energy is what we refer to as a state function. Another way to think about it would be if you were climbing a mountain if you were to climb straight up the mountain to get from point A to point B, the distance traveled would not be a state function because you could go in a direct route from A to B, or you could go back and forth on the mountain, arriving at point B. So the distance traveled would not be a state function. However, your altitude would be a state function because it doesn't matter how you arrived at point B, your change in altitude would be the exact same between points A and point B. So altitude is a state function, distance traveled would not be a state function. Here's another example that would illustrate the difference between a state function and non-state function. If we have two batteries and one battery is being discharged through a resistor, and so as the current goes through the resistor, heat is dissipated as the current goes back to the other side. On the right side, the current is going through a fan, so the fan is moving air and then going back to the current's going back to the battery. So on the left, all of the energy that's being discharged from the battery is being discharged in the form of heat. On the right, a significant portion of the energy that's being discharged is in the form of work being done by turning the fan, and some of it is being released in the form of heat. So heat and work, or Q and W, are not state functions. They depend on the pathway that you take. However, the internal energy of the battery is a state function. It doesn't matter which way you dissipated the energy through the fan or through the resistor, the change in the internal energy is the same.